Thanks everyone for coming. Thanks so much for the invitation. I'm very excited to be here this week and also for a couple months. So first, I want to tell you about coarse geometry of big mathematical groups of graphs. And this is all work joint with Hoganson and Sanghoon and Kwak. But first, I'm going to kind of be like Sebastian and first tell you about some small groups. So two small groups before we jump onto the huge groups. And I want to think of these groups both as kind of coming from some topologist or geometric group there. So coming from some object and then studying its symmetries. I start with some object and then a group of symmetries. But maybe then this group of symmetries is kind of a little too complicated. So we'll do up to some equivalence. So the first one has already been mentioned a couple of times, I think, is the mapping class group, which I'm going to think of the objects as surfaces. So a surface like this, or maybe a genus 3 surface. Maybe allowing a puncture if I want, whatever I want. Okay, and then the symmetries will be homeomorphisms. Maybe orientation preserving if I want, but that's not actually mapping. I'm going to write it. And okay, well, we already saw we can study the homeomorphism group, but now I'm going to, the other side, instead of studying the full homeomorphism group, you can study the mapping class group, which is you do up to homotopy. And so this is nice. Kind of over here, as it makes the group a lot more tractable. So when we have these finite type surfaces, we see only finitely much topology, it becomes finitely generated, hence me using the word small. We'll see in a second how you jump up to now huge groups. So this is one nice class of groups, and another class of groups, a geometric group theorists like a lot, is you start with, instead of a surface, you just start with the free group. So this is the free group on n letters. Okay, and then what's a natural symmetry group of a group? Well, of the free group, it's the automorphism group. And then a natural equivalence to do is up to the inner automorphisms, where you can think kind of you're modding out by conjugation. Right, so what are these? These are the subgroup of inner automorphisms, or all the automorphisms that just come from conjugation of the elements. So this is something we can understand pretty well. So if we kind of throw those out, we're left with the interesting things, and this we call out effect. Okay, and there's this rich dichotomy, this rich dictionary back and forth between the study of these two groups that goes back now several decades, and it's some, I don't know, maybe you can call it classical. And this dictionary, there's a lot of kind of there's some loose back and forth where they kind of both of these groups act on similar objects like the type-muller space or the curve complex, and there's some notion of outer space instead of type-muller space, and there's a notion of a curve complex over here, and you can understand a lot about these groups. There's sometimes even maps between them, and you can really do a lot by kind of comparing and contrasting these two groups, and a lot of the methods work for both groups. So this is kind of in the small world, the not huge world, and this is a super rich back and forth, but this is a conference on huge groups. So I was already told my handwriting might be too small, so if I continue making it small, please just yell. And also if you have any questions, please just, I might not notice your hands, so feel free to just yell out. So let's start with two huge groups. So the one here will be the big mapping class group. Well, I mean, not the big, but big mapping class groups. And what is this? The group is defined in the same way. So the actual group is the same, but it's the objects that you're thinking the homeomorphism group of. So here, there was a restriction that I deal with a finite type surface, or that the fundamental group is finitely generated. Here I allow for, I don't just allow, I almost want kind of infinite type surfaces, right? And the definition there that just your fundamental group is not finitely generated. So you could have something like this with genus going out one side. You could have some crazy like tree-like thing that just keeps branching forever and ever and ever. Maybe you have a bunch of genus. You could have, I don't know, some mixture of this. Maybe kind of here it branches repeatedly, and maybe here there's genus going down, and maybe here there's punctures. You can really do whatever you want. So you start with a surface like that, and then you can just define the exact same group. So it's the group of homeomorphisms. up to homotopy. And this has become kind of a huge group of research about these huge groups. And why are these huge? So they're so huge because they are uncountable. Well, these are maybe some reasons. Uncountable, i.e. not finitely generated. Even worse than that is they come equipped with some natural topology. That topology is not even locally compact, so they're not even compactly generated. So this is why now we jump into the world of huge groups. And so now, kind of the question that is one of the goals of the talk is what should go over here. Right down here in this more classical setting, we have these two groups that are friends, and it's very beneficial to kind of study them both together. And a lot of techniques can go from one to the other. So what should go over here? Kind of what is the big out FN? Is there a natural kind of analog? And you might stare at me and say, okay, well, here's an n. That's a number. Why not just let it be infinite? Sure, that is an answer. I kind of want to say a little bit why I don't like that answer so much, but one answer is you could just take out or ought f infinity. So take the free group on countably many generators and look at its automorphism group or look at its outer automorphism group. This is a perfectly good group to study. There's kind of two drawbacks, which would be a little bit as to why my talk is not going to be about this group and about some other groups. One drawback is that, well, there's only one of them. Okay, maybe that's not so bad, but if you want an analog for the surfaces, right here you have a huge menagerie of surfaces and therefore a huge menagerie of groups, right? There's in fact uncountably many surfaces of this type, or not of this type, but uncountably many different surfaces. And so you get uncountably many groups, and you can start asking, like, how does the topology of the surface relate to the structures of the group? Here you just have one, so that's like a little unsatisfying. And it also means that if you're trying to kind of adopt tools from one side to the other, like, it's not going to be as fruitful. Another drawback is maybe a little bit more of a, this is maybe a source of opinion. This one is maybe also a source of opinion, but slightly more convincing. Is if I'm a geometric group theorist, I want to study, groups up to their geometry, their coarse geometry. And one downside to this group, so this is due to myself, the same in Hoganson and Sanghoon Kwak, is that these groups either ought or out. So they are, and I'm going to put this in quotes because I'll explain a little bit what I mean more precisely, but they are quasi-isometric. Right? There is a lot to kind of unpack in this, and that will be kind of the goal of the second half. Well, not for these groups in particular, but what this notion of quasi-isometry is. But it really is saying that you cannot put a good metric on this group that's unbounded. So if you want to think of groups by their geometry, like these is, I don't know, then we're done. We know everything. So I kind of don't want this to be the analog. I don't just want to take this n and let it go to infinity. But another way to see this group that kind of is a little nicer, if you like thinking topologically, instead of purely algebraically, is, well, instead of thinking about the free group on n generators, think about a graph, a finite graph. Or just think about a rows, right? So this has fundamental group F3. And now instead of automorphisms of the group, you can study homotopy equivalences. Homotopy equivalences is gamma, right? So any homotopy equivalence is going to give you an isomorphism on pi1. So it'll determine an automorphism of the free group. And then there's this, what is the nice up to here? Well, it's up to homotopy. And why? That's part of that's because we don't really want to worry about like where the base point is. So we want kind of unbased fundamental groups. And then this is also kind of the right notion that'll get rid of that worrying about if you kind of let all your maps be up to homotopy. So now instead of kind of staring at like the algebraic pieces, the non-mean, and saying let's go to infinity, let's instead look at these pictures and let's go to infinity. Not let's go to infinity, but let's make a big analog. So what our objects will be now are kind of infinite type graphs. So maybe something like this. Or something like this. Or who knows what, maybe just something like, you know, where when I'm kind of putting a thing here, I mean, these continue on forever. Or maybe something like this. And we want some restrictions to kind of keep us in the world of things that aren't like too crazy. So what do I mean now by kind of a big graph? Well, I just want a gamma that is locally finite. And let me just say a word. When I say the graph, I don't mean that like these are the vertices and edges. I'm not going to care about that. I really just mean like a one-dimensional CW complex. So the actual like graph structure isn't going to matter. Because I'm going to do things like homotopy equivalences, which don't respect where vertices are. Great. So now there's this big world of objects here. And now we can think a little bit about the symmetries that we want. And one tool that's going to kind of help us is that, okay, we can think of just like all these possible graphs, and there's lots of them. But kind of just like over here, I guess I didn't say this, right down here, we have classification of surfaces. That's nice. That's great. That's incredibly powerful. Up here, there is an analogous classification of surfaces of these types. That I'll say a little more, but that's incredibly powerful. And there's also a nice classification here. So classification for graphs. So really for locally finite, well, actually you don't need infinite, just locally finite. This is due to Ayala, as in Quintero, 1990. And this will also kind of be a nice answer to the drawback number one down here of there being only one of them. And what does it say? It says the proper homotopy equivalence type of gamma locally finite, so a locally finite graph, is determined by a triple. So the rank of gamma, the n space of gamma, and the n's accumulated by loops of gamma. So what are all of these? This rank, I really just mean the rank of the fundamental group. So this is some either non-positive integer or potentially infinite, or infinity for me is just uncountably infinite. This is kind of a space of n's. So it really is all the ways to go to infinity in your graph. And this is defined kind of in the usual way you can define n's, but really you can just think of it as, okay, well, what are the different ways to go to infinity? Well, in this one, there's only one. Right. Over here, there's four. Right. Over here, well, now you can like branch, right? Imagine this tree goes forever. So it's something a lot more complicated. And in fact, it'll look like the Cantor set. So this is actually a topological space. You can topologize it. And if you want, you can take it as the inverse limit over compact subsets of the connected components. What did I say? Of the complements of compact subsets. And this will always be a closed subset of the Cantor set. Cantor set. And in fact, part of this theorem is that any possible closed subset of the Cantor set is realized. You give me any one, there is some graph that has that n space. And then this is the subspace of n's accumulated by loops. So you can think about it like in this inverse limit, just taking the pieces that always have infinite rank. Or in the picture, you can just kind of think of like, okay, well, as I walk towards this end, I'm just always seeing some actual loops in my graph. So like over here, you know, you have one end accumulated loops. Over here, maybe let's erase this one and say, you know, this whole half of the tree is, and this whole half is not. And then over here, you have like two that are not and two that are. Okay, and so what this theorem says is that you give me any triple, and where now this is a pair of topological spaces. So, you know, it's classified by the information of this just number, and then this kind of pair of topological spaces. So if you have two graphs that have the same number here, and there's a homeomorphism between their n spaces, well, then the graphs themselves are actually related by a proper homotopy equivalence. And kind of one nice punchline, so this kind of resolves, I don't know if I can say it resolves, but kind of drawback one nicely, because it's kind of the same classification as for surfaces. Where for surfaces, what is the statement? It's you just take the homeomorphism type of a surface now is determined by its genus, its space of n's, and its n's accumulated by genus, defined really in the same way for the n spaces. Where now just rank is playing the role of genus. So that's one nice thing, because now we actually do have, like, right over here we had a rich collection of surfaces and hence groups, and now we have equally as rich collection of graphs and groups. And this will also lead to kind of what is the group now.
When you define the n plus group, do you really mean just one edge to the group, or could you do with bounded finite graph?
That's what, yeah, I really mean, yeah, I don't just mean like loops as in little loops. I really just mean like any rank of the graph. So like this would also be one end accumulated by loops. Yeah. Thanks.
And in the surface case, what is the third element?
It's n's accumulated by genus. So it's if every time you cut up a compact piece, you see genus and towards that end. Yeah.
One more question.
Yeah.
Sorry, so just to put a final point on this, the difference is we're looking at halves that sort of leave every compact component versus sort of existing. Yeah, but
So I'm not sure I followed your question, but what all you're doing is really, you can really just think like, what are the different ways of going to infinity? Meaning like, as you remove compact sets, like what are the leftover pieces? So as you keep removing compact sets here, like, fix some like exhaustion by compact sets, well, as you keep removing them, you only have one complementary component. Whereas over here, like maybe this is a compact set, you remove it, you have two components. Now this is a compact set, you remove it, there's four components. And if, this one, as you keep removing things, you will keep getting more and more components. So you'll see like infinitely many ends at least. Or like over here, I mean, once you remove this compact set, like now you only see four components ever. Did that help make sense?
yeah.
We can talk more about it. It won't be terribly important for the rest of the project. So now we're ready to say what the group is, and this, now you can't really read this too well. So those are our objects, and kind of what's the group or the groups? The kind of answer to big mapping class groups of graphs. So this is a definition due to Algom Kfir and Bestvina. And it is take now the mapping class group of your graph to be, just like over here, we took homotopy equivalences. So you'll write here first, homotopy equivalences. Except for that's too loose. Because if you only take homotopy equivalences, you lose any information about what's happening at infinity, about the ends. Because, for example, all three of these graphs all just contract down to the rows with infinitely many petals. So that's like too loose. So what you really need is the word proper. You'll take proper homotopy equivalences, where this means pre-image of compact sets are compact. And that was also exactly the condition you had down here. It's not just the homotopy equivalences, right? That's determined here by the okay. So you take the group now of proper homotopy equivalences. And now again, you want to do up to homotopy, except for that's not the right thing. You should do it up to proper homotopy. So now this is our big analog of out FN. And so, I mean, one note is that, and I kind of said this a lot when I did the green, if you feed in a finite graph, you do just get back out FN, where ends whatever the rank of the finite graph is. So that's nice. It really does extend the mapping class group. So now let's just see some examples of what elements of this group look like. So the first two examples will both be on this graph. So what I'm going to do is I'm going to describe these maps by kind of cheating and like saying what they do on the fundamental group by like labeling these loops. So, but then I'll also draw a picture of what it does. So the first one will be this F, I'm putting a star here because really I'm telling you what the map does in the fundamental group, but then I'll draw an actual graph map. It's just going to send A1 to the loop A1, A2, and the identity elsewhere. So what is this going to do? It's going to be the identity on everywhere except this edge. And now I'm going to map this edge over this. So that's something you can do. That's kind of an element that sort of comes from the finite type out of n. Not too surprising. So this is kind of the F that does this. Okay, you can take G star is just going to be, you do this infinitely many times. So A1 goes to A1, A2, A3 goes to like A3, A4, etc. And then you have the identity on like A2 and all these even ones. So what does this picture look like? It's the identity everywhere outside of these orange ones. And then what does it do? Well, it just is doing this picture locally everywhere. So it's sending this first loop to this path. This one, this whole edge, this loop, this edge is fixed. This loop is sent to that path, and it goes on forever. So this is kind of a new, like, infinite type phenomenon. Okay, what is another example? Two more examples. So 3, you can do something like a shift. So let's say I have like this graph, where then I also have something coming down. I can do a map H that just takes this whole piece and just shifts it over by 1. And so, there's something a little weird going on here, but what happens is, well, if you shift by 1, like this little segment can just get stretched over here. So kind of the thing about homotopy equivalences that is both like very nice, but also makes it hard if you come from the world of homomorphisms, is that they don't have to be injective. That's why it feels sometimes like you can do weirder things than in the group world and then in the surface world. So number 4 is something like this. So now take the graph so now this is just a ray going out. And what you can do is you can take, right, again, label these by like A1, A2, A3. You can take this little segment and just write some word in the free group in here. Let's say just write like A1, A3. And then you can do the map that sends, that just takes this little piece and kind of drags it over A1 and A3. I want the map to be the identity everywhere except for on this piece. And then this segment is going to get dragged over. So this is something that's kind of weird and different. And one place where, okay, if we did things up to just homotopy, well, this would just be the trivial map because this is defined as incontractable. But because we're doing proper homotopies, like you can't undo this mapping because you have a whole array here. These are some examples, questions about these. So let me know if you can't see something on the boards, if one is blocking the other or something. And these are all examples that lie in a nice subgroup. So these all lie in the pure mapping class group, i.e. they fix the ends. And I'll refer to this as the pure. Okay, I think I can now erase this over here. So now the first thing to note is, as I kind of told you, that these are huge groups, but let's actually see that they're huge. Well, what do I mean by this? All right, so for example, they're uncountable. i.e. they're not finally generated. Not i.e., but that implies they're not finally generated. One way to see this is by this example of G, where I did this kind of map 1 over 2 and do it everywhere. Well, you could just imagine like leaving out some of these. So you can get an embedding of like 0, 1 to the n into your group by just taking like subsequences of these pictures. Okay, but they are equipped with a topology. So you can equip them with kind of a compact open topology. I'm putting this in quotes just because you have to be a little more careful in setting things up in order to get something nice than you do with homeomorphism groups, but it really is this. And if you want the details, I guess this is in the Algom Kfir and Bestvina paper. And how do you think about this? Well, a neighborhood basis about the identity is given by sets of the form U sub k. So for k some compact subset of your graph. Well, you're just looking at the F in the mapping class group of gamma that fix k. They're actually identity on k. Okay, and here I'm being a little sloppy remembering equals, but everything is up to proper homotopies. So yeah, properly homotopic to a map that is the identity on the graph is what I mean. And preserves components of gamma minus k. So what does this look like? What is something close to the identity? Well, you just hand me some compact set, say this one, and as long as you fix this pointwise, or you're properly homotopic to something that does, and you don't mix up the components, right? And that seems maybe like a weird condition at first, but it really does come from the fact that like homotopy equivalences don't have to be injective. Like if you're talking about homeomorphisms and you fix this and you're the identity here, then for free you're gonna not fix the components, but you're gonna like not permute the components. But right, what could go wrong here is you could have a map like this, right? Like you might have a map that is the identity on this subgraph, but actually does send this loop like over these, something like that, and that will not be something that's close to the identity. Right. So what does it mean for things to converge to the identity? It means that, well, you just take bigger and bigger, you have some sequence converges to the identity if it's just the identity on larger and larger subgraphs. Right? Or when are two things close? Basically, they agree on large subgraphs with this slightly extra condition. But okay, this topology also kind of contributes to the sense of hugeness of this group. First, I'll say it at least is not like so bad, but this turns into a Polish group, which means that the topology is separable. So it has a countable dense subset and completely metrizable. So it does admit some complete metric. If you want, you can think of this as not too bad. But it's still huge, but it's not locally compact even. Right, that's kind of the next best thing. If you're not finally generated, you might, hope that you're compactly generated. But it's not that. So they really are huge. And if you want, these are all of the groups are topologically homeomorphic to R minus Q, to the irrationals, just as topological spaces, right? Not at all observing the group structure. So these are really big groups, they're huge groups. Great. Okay, but now that might give you some fear, like it gave me some fear, which is, okay, I like finally generated groups. I like word metrics. I like quasi-isometry types of groups. How do we ever do this with these groups? So I'm actually going to talk about a little bit about what Sebastian mentioned, where there's kind of this other route to make this work in this setting. So how to do geometric group theory. So there's this framework developed by Christian Rosendal, and the idea is you replace kind of the notion of finite or compact. So I should say there is a theory of word metrics for compactly generated groups, and kind of a well-defined notion of when a group has like a well-defined metric if it's compactly generated, but these are not compactly generated. So what Christian does is he replaces this notion with a more general one that is kind of exactly the right or exactly the condition you need to run the classical like Milnor-Schwarz type lemmas. General definition. So what is the definition? So I pre-wrote it because I wanted to say all three things. So these are three equivalent definitions. So you say that a subset of your Polish group is coarsely bounded. That's going to be the thing that replaces finite or compact. If one of the following holds, either given any left invariant compatible metric on your group, the diameter of the set is finite. So no matter what metric you have, right, if you want it to generate the same topology in the group, your set will always be bounded. Okay, or, right, given any continuous action on a metric space, the diameter of any orbit under that point, under that subset, is bounded. These is not too hard to go back and forth between them. And this third one, right, these two are kind of how would you ever check these conditions? You need to consider like all possible metrics on your group or all possible actions on metric spaces. This next one is the one you can actually check. And what does it say? It says that if I hand you a neighborhood about the identity, then you can find finitely many steps so that you can cover the whole set. Right? So given some neighborhood about the identity, so some small set, here the identity, I can hand you just finitely many elements, other elements in G, so that you can write anything in A as some nth product of the finitely many things and the small things in the topology. So this is the condition you replace. And so if you feed in like a finitely generated group into this, well, the coarsely bounded sets are exactly the finite sets. Or any compact set is for free coarsely bounded. Great. And then what is the punchline of this? I did not think about this part. Can't raise this board. The punchline is that this is the condition that you need to run the tools of geometric group theory. He's kind of isolated the right conditions you need. So if you start with a Polish group, it works in more generality. Let's just pick up my statements. Well, if G is locally CB, meaning it has a neighborhood about the identity that is coarsely bounded, same as like locally compact, and CB generated, here I mean you have a generating set, an algebraic generating set that is coarsely bounded. So notice this definition is not for like subgroups, it's just for subsets. You admit some generating set that is coarsely bounded. This implies that G has a well-defined quasi-isometry type. Meaning what? Really, it means that, what is the usual version of this is you have a finitely generated group. You give me two finite generating sets, then the word metrics that they generate, or the word metrics they define, are related by a quasi-isometry. What this is saying is you give me two CB generating sets, right? There's a way you can define a word metric on the group now using those, each of those, and those two metrics are quasi-isometric. Closely CB means that you have a neighborhood about the identity that is CB. There is some U for this. And then you can also get away with a little bit less. So if G is only locally CB, that gives you a well-defined coarse equivalence type, which is just a type of weakening of quasi-isometry. So even if you just get to locally CB, you still have things that you can do. You can start studying geometry. And so this is what we did. So what does this do? It gives you this framework that if you can check these conditions on the group, you can say, okay, when can we actually study these groups from the perspective of geometric group theory? So I should say, I should give some credit that kind of this was first applied to surfaces by Mann and Rafi, applied this to surfaces. And I'll say out loud more what their results actually are. These ideas to surfaces. So by surfaces, I mean big mapping class groups of surfaces. So what we do, we completely classify when the pure mapping class group of a graph is either TP or locally CP. And kind of all cases show up, right? So this is one thing that's kind of remarkable is even though these are huge groups in some sense, there are examples. So I'll just do an example. Like an example here. I guess I'll do more examples in a second, but I'll just, if you start with this graph, there's one-ended. This one has a CB mapping class group, right? So in some sense, these are huge groups kind of topologically or algebraically, but geometrically they're trivial. Remember, if the whole group is CB, so what do I mean by CB? I mean the entire group is coarsely bounded. So that means that any possible nice metric you put on the group has bounded diameter. So I should say the thing I wrote before about infinity and off infinity, this is really proof of CB. Okay, but there are also examples of ones that are not CB, there are examples of ones that are CB, or not are not CB. What Man and Rafi do is they do it for the full mapping class groups of surfaces up to some conditions, and they also get CB generation. But for us, what we did is, having a locally CB, we could already start doing some coarse invariance. And that's kind of the second piece, is that if the rank of gamma is infinite, and this pure mapping class group is locally CB, we compute the asymptotic dimension. So this is some coarse notion of dimension, and one thing is that it's not just a Q-line invariant, it's also whatever this coarse equivalence invariant is. So at least having that is good enough to start computing this, and we see that it's either 0 or infinite, and it's 0 exactly if there's only one end accumulated by loops. Okay, and what are these conditions? Okay, well, the rank infinite condition is because we don't know asymptotic dimension out of n. So like, if we could prove it for finite, I'd be talking about that because it'd be a much bigger result. And then locally CB is just to say, okay, where does it even make sense to use the word asymptotic dimension? And then instead of kind of saying anything about the proof, I kind of wanted to, or the actual classification, I kind of wanted to just write some examples and say, like, what is the behavior that gives you various things? So I'll pause on questions.
Well, if there's no ends that are accumulated by the units,
Then you're not infinite rank.
oh, okay.
Yeah. I mean, but some of those, so if you have 0 rank and you look at the pure mapping class group, you're just trivial. So there are like some things where it just boils down to something trivial, but then some things where it boils down to something very hard. So, some examples. Like, how do you do this, right? So here's an example. This graph. So this graph, you look at its pure mapping class group. We want to first ask, is it CB or not, right? Is it coarsely bounded or not? And then ask, is it locally? I mean, if it's coarsely bounded, it's definitely locally. So this one is not coarsely bounded, so it has some interesting geometry. And what is that geometry? Well, it really does come from this shift map. I don't know why I redrew that, but so you can define a continuous surjection homomorphism from the pure mapping class group gamma to Z. And then you have an action on an unbounded action on some space because you just act on Z. Okay, and it really does come from, you take this picture and you basically are counting how many loops you shift. Except for you can't just do that. You have to like do more work and you have to kind of define the map algebraically. So this kind of comes from some ideas of, you use some out of n tools. Okay, and now I think okay, I'll say, I think I ran out of time and I don't want to run over. So if you want more examples, then please talk to me. Sorry, not use the 45 as opposed to 50.
Question. So is out of F infinity realized as any of these big entities?
It's realized as, so you can do out F infinity if you take just homotopy equivalences, not proper ones, of say like this infinite petal
That
rows.
was not locally finite.
Yeah, so the problem is now like you'll lose you'll lose any local finiteness. But as to whether you can actually
No, I meant.
Yeah, like
Is it realized in your setting? Where
yeah, that's a good question. I would guess no, but I don't have immediately any like actual way to prove that. So I think that's actually, yeah, kind of hard. Or maybe the question is, does out F infinity like embed into any of these groups? Yeah, I don't, off the top of my head, have any way to rule that out. I would guess no, but also maybe yes, because these bigs are the groups are so big that you can just like shove whatever you want into them.
What was supposed to be the second example?
Yeah. So the second example is where you get another way to see non-CB-ness, where you see this like dimension zero-ness sort of. So I guess it's also, whoa, I'm gonna be the one who breaks it, is something like this. So I already said kind of if you don't have this tree over here, if you just have the one-ended thing, then you are CB. But even just putting like a tree over here is enough. And the way you can get not CB-ness, so the way I got not CB here is here was like a nice action on some space. Here, I'm not going to immediately build a nice action. I'm actually just going to, you can just build like a nice metric on the space. And you can build a length function on the space by just saying, okay, you give me any map, it'll only have like bounded support on this half of the graph because we're looking at proper maps. And so like they'll all look like this example, I don't know, 5 that I had of the, you take this segment and you wrap it around loops. So you can define an unbounded length function that just counts how far out in this tree do you have to see the support of the element. So L from the pure mapping class group of gamma to R, or let's say R plus. And you can use this to actually just define a metric on your group. And then kind of part of the magic of how we got something like this out is that it turns out this metric will actually be just zero hyperbolic. So you can like do even more with it. Yeah, so you can see kind of either you can see these like shifts, or you can see some like kind of unboundedness coming from over here, but like not too bad. So it kind of puts your groups in like 3 categories. You have the trivial ones, geometrically the ones that are CB. You have the ones that are that are ones that are huge, like with these shifts. These will be the same ones that, okay, I shouldn't say huge, are really huge. The ones that have infinite asymptotic dimension will be from the shift things. And then there's the third behavior that kind of fits in the middle. So there's examples of these that are non-CB, and it comes from this slide. And this is something that doesn't happen in surfaces. You can like measure in this way. Yeah. Thanks. Hoping somebody would ask.
Okay, so we'll have coffee break now. We meet corporate back. Thank George again.